Hello, welcome to the channel. Today we are going to learn about Autograd. So, as the name suggests, Autograd just basically does simple stuff for us like the back propagation we learned. Autograd. So, in the previous videos, I covered topics related to this, the chain rule, and in back propagation, we just go through the whole set of process again, like doing the weight calculation with the bias and calculating the loss in between and adding the activation function and doing all this in the reverse chronological order. So what at Autograd does in PyTorch, it basically makes our life simple. So what Autograd does is, let's say I perform some operation from 1 to 3. So what it will do is it will take an ASDG, acyclic, I think directed graph. If you want to know more about the graph and how it works, you can go through this. Yeah, it is DAG. My bad. Directed acyclic graph, and what it is really is, there are directions between each nodes, but it is not cyclic. It looks cyclic, but it is not cyclic. And what it does is it gives us the functionality to calculate this differentiation based on the stuff we have, and it's just a single command like backward. So basically, this makes our life easy. This is how the A, I mean DAG looks like. It takes all the operations and performs it in the backward again, but with derivatives, and it uses Jacobian vector product. So basically, Jacobian is something like this. We'll take a bunch of derivatives, and we do the matrix operation and arrive at a single value. Here there are two kinds of stuff like forward and other is reverse. Basically, one is like for bigger data sets, like inputs to outputs, and reverse is like output to input. So for this, I made a notebook. Here I'm going to cover the syntax, whatever stuff we are using, and gradient accumulation. To make life simple, I am also explaining how Sigmoid and ReLU works. So basically, I'm just adding Sigmoid and ReLU for a network, but we're showing the stuff. I mean, we're showing the loop that is happening around, and here I took these as imports. Torch.neural network and torch.neural network functional as f. Basically, we'll take a tensor and it has a value that is scalar. So scalar is like something with some magnitude, like some distance, but no direction. So it doesn't have any like dimensions or something. And I have added something called requires grad equal to true. What requires grad equal to true does is it tracks the operations that are being done to this tensor or scalar, whatever value we take, and they it is constructed in an DAG, directed acyclic graph, and so whenever we use something like backward, it will does the calculation automatically. It is there to make life easy, and grad fn is to check what it holds at that point. Here grad fn holds the power backward. That means I have used, I mean, I have squared this, and this is what it holds. It holds this powered operation, and we can compute the gradient. Basically, I'm using backward. That means, like, let's say we have a value x square, and I want to calculate the derivative of this in the in further steps. The backward value will be 2x, and here I applied to backward, y dot backward, and the gradient value would be like 4. But let me replace this with 10 just to get a sense of this. Here this is the value, it is 20, and this is for showing up the graph, each and every operation that is done. So these are just like stuff that is going through in between, through and in between the graph. Like A is a node, B is a node, C is a node, and each of them will have a connection. And as it is acyclic, I don't really get into a loop, but I arrive at a solution. It is basically a chain and a loop, most likely a pendant. Here, each operation is taken into consideration. One does the power, other does the multiplication, and other is add. Whenever I do backward, I'll arrive at a constant because these are simple equations. There is nothing much to do, and it also works with tensors. Tensors are basically these 1 dot, 2 dot, 3 dot, and we need this because we can't operate on scalar values, because weights will be like these input, outputs, and inputs, and these will be in multiple. I mean, there will be multiple values around that, and here it is an example. And whenever I do x square, and the loss is the sum, the square is applied to everything, and whenever I do backward, it is 2x of everything. That will be like 2, 4, and 6. This is the output, and backward does the differentiation for us, partial differentiation. Yeah, partial. And there is this thing called gradient accumulation. So basically, what gradient accumulation is, let's say I performed an operation. Let's say we have x square, and I did the backward. Then I arrive at a value 4. And if I try the x square again and do the backward, I won't be arriving at 4 again. I will be arriving at 8, because in the first operation we got this 4 right. This value is accumulated to the next layer, so that will be the sum of it. And to get rid of it, we'll do something to to clear this stuff. And here are the values. We arrived at 8, but it should be 4, and we didn't clear this tensor again. And to clear this, we are going to set the gradient to 0, that is grad 0, and here we will arrive at 4, 4, 4. These are the outputs. And in the next few things, I mean, next steps, I'm going to explore. I mean, I'm going to explore the Sigmoid and ReLU, but with Autograd. If you don't know what Sigmoid and ReLU, there is a video on my channel. You can check. And to give a simple, easy thing, Sigmoid will have values between 0 and 1. I mean, use it to maintain the values between 0 and 1. And ReLU is like 0 to positive values. That will be the like max of 0 comma y. This is the simple thing, and we are going to apply it here. I take a tensor, that is the x. This is my feature matrix. These are the weights, and in the initial operation, I have to calculate this, the z, sum of it, and I have a target. This is the value I need, and I use this to predict the loss. That means the difference between the target value and the predicted value. I mean predicted value and the target value, and I square it because I need a greater output and positive values. And in between we use this torch.sigmoid. Here applying sigmoid is quite easy compared to the versions we have seen till now. It's just sigmoid, and another one is just torch.relu. And I have did the initial calculation, and I can do the loss dot backward. That means it will apply the chain rule and give us some output. Here are the values of these. The prediction value is this, the loss value is this, and the gradient value is this. And the same applies for ReLU 2. I do the prediction minus target f dot ReLU. Here, the interesting thing is we are using f for ReLU because that is a functional property, and it does the same thing. There is this thing called ReLU dead zone. In the previous videos, we have learned about this He's algorithm and he Golomrot and other guy, I forgot his name. These are for weight initialization. Sometimes these weights, let's say I took a negative value, and this will make the ReLU value as 0 because we are calculating the value 0 and the x. Basically it is 0. If we arrive at 0, the neural network will turn off because it is not something like yes or no. It is saying just I don't know the values. I mean, I don't know this. That's what it is saying. There is a difference between no and I don't know. The same thing applies here. And whenever I try to draw a perfect circle, I arrive at this. I want to do that. I love that. And this is the ReLU dead zone. Here, as you can see, I took the weight as minus, and this will make the gradient 0. And I want to arrive at a prediction at any point. To avoid this, we use that weight initialization algorithms. They are like they use standard deviation. In some video you can find in the playlist, the GPT playlist. Here, to save some time and to show how things work, I have made a neural network. Here it takes the linear, applies ReLU, does linear again, and applies sigmoid. And if you are confused what linear is basically this weight to the x, and if we have some bias, it will be this bias. This is the step that we do linear, and in the first step we calculate the w1, and in the next step we calculate the loss, and in the next step we'll do the w2 because there are like layer and a hidden layer and output. And after that I'll apply the sigmoid. So this is the first step, and what I'll do is I'll just use nn dot sequential and define these steps. After that we'll just do the backward, and the loss is calculated backward, and all these operations are done in the backward fashion. And this is the model x. I mean, for every prediction I'll do this. I'll do the linear ReLU sigmoid, and after that I'll check the target, and loss dot backward will do these steps again and again. As this is a single loop, we'll arrive at the solution fast. And basically this is a loop, and in this loop I'm showing what parameters I have, the bias tensor weight. And this is a mini training loop. We apply optimizers in between. I'll cover what optimizers are in the coming videos. This is the SGD, stochastic gradient descent. and it is it does optimization basically, and it is like there is also the thing called Adam. I'll cover this in the next videos, and we'll use this epoch. That means the times I do the training. In the first step, we did this. Now we will doing this in a loop in 20 iterations. So after 20 iterations, we arrive at a prediction loss. See here, for each epoch, I am checking the loss. Once I arrive at a good place with nominal loss, we'll wrap up the training. And this is for today. We learned about PyTorch Autograd. It is one of the greatest things that is there. And sometimes we don't track the gradient required grad. The cases where we set this as false are the cases what we call inference. That means we don't keep track of the input and outputs in between layers. So it's like I pass an input, it goes through all the hidden layers, and I'll get to the output. There is no passing of messages in between these things like we do in training, because we don't do training when we want an output. So during inference, we will turn that off, the required grad. And these are the stuff we need to know about required grad, because in the coming videos I'm going to explain about the normalization that is there. There are like batched normalization, layered. These normalizations are quite important. We're going to learn about these things, and I'm going to make a practice video that is there in Neetcode. And finally, thank you for watching. Your support means a lot. In the last video got quite many views. Please like, share, and subscribe, and I'll be back with more videos. Thank you for watching.